let's go ahead and get started. All right, so for the first one, again, it's always good to do these in steps. So the sodium cyanide is a good nucleophile. That's going to substitute for the bromide, right? So I'm gonna have an SN2 style reaction. And then the sodium borohydride, lithium hydride, and water. That's gonna do a reduction of the nitrile, okay, to add a carbon and the NH2, right? So the result here is to add one carbon and then the NH2. So we do make the primary amine, but with the carbon. The second one, and let's go ahead and, this is all in one pot, but we'll go ahead and divide it out so you can kind of remember what we were doing here. Okay, the process here is first, we make the imine or enamine. In this case, since it's a primary amine, we make the imine. Right. And then the sodium borohydride, sodium borohydride is a special reagent. Ooh, and there should have been a 3 right there to reduce that. Right, and so my answer would have just been this. Okay, questions about that one? Okay, so that's reductive amination. And then the last one, this is the Gabriel synthesis, right? So the first thing we're going to do is abstract that proton, right? So that gives me the nitrogen negative. And then that reacts with my electrophile. Right? And then the hydrazine liberates that nitrogen. Right? And that's the product I'm focused on here. The other product, so if it ever says, don't worry about the byproducts, especially online, right? This is the byproduct. Our focus is that molecule. So when we use the Gabriel synthesis to make an amine, we're looking for the amine, not the succinimide byproduct. Right, questions about those? So you notice I put the quizzes already up. You'll see some changes, but so that you know the date. So next Tuesday, and again, after class to 10 o'clock, right? So find yourself 15 minutes in that time span. And then the last day that we can have an assignment based on the pre-final week is going to be the Tuesday. So that one's probably going to be more review. So the Tuesday, December 8th, maybe that's 8th, is the other one. And then our exam was December 2nd. Okay. All right, we're going to finish. We're going to get as far as we can to finishing the chapter today. So the next section in this chapter is Hoffman elimination. If we remember, if we have an alcohol and we want to eliminate that alcohol, the first thing we need to do is turn it into a good leaving group. So we could do something like the tosylate, right? And then we could add a base. And that base is going to eliminate, right? And this is going to give me a Setsef product, right? Which is the most substituted. So we've seen that. This is review, right? This is nothing new. With Hoffman eliminations, we're going to start with amines. And the first thing we're going to do is activate those like we would with the tosylate, but we're going to activate it with methyl iodide excess. Right. The other reagents you might see here would be CH3I and something like potassium carbonate. That's going to fully alkylate. So remember we talked last time about the fact that alkylation of amines, every time you add a carbon, it makes the next carbon easier to add, right? So it'll continue to do that. So we end up with this quaternary salt. Let's see if I can get this. I can give myself a little bit more room. Yeah. Sorry, you can't do that in your notebooks. Here we're going to use silver oxide, so Ag2O in water and heat. And here we're going to eliminate to give us the Hoffman product. So since the, similar process, right? We take our amine, we activate it. This time we're activating as a quaternary salt. And then we're going to use this silver oxide and water. What happens with silver oxide and water is you actually make a silver hydroxide. So this compound is not stable, right? So what you do is you make it in situ. So you take this silver oxide, which is kind of a paste, and you add water to it, it makes a silver oxide. What's happening in this is what we would expect. You're getting an elimination with that hydroxide. And why you use the silver, so let's say we have the iodine out here, right? So this ends up giving us our elimination product, plus then water, plus the ammonium. And I used to do a similar reaction all the time. This trimethylamine here is actually gas. Plus the silver iodide, and the silver iodide is a solid. So it falls out of solution. So the reason they use the silver iodide here is that ammonium compound is a good leaving group, right? So if we look here, right, this is a great leaving group. If I had iodine, potentially it could knock that off. So what we do is we isolate it as a silver oxide, okay? So this is what the reaction, the mechanism is occurring is just reusing the silver oxide, and we get a gas and a solid. So this is a really nice, clean reaction to do this. Why it goes to the outside has to do with the transition state. So we're getting the least stable product, right? The terminal product. So therefore it's the transition state that's going to be the driving force here. So if we look at this hydrogen, and remember our Newman projections. Right? So if you remember last semester, so I'm looking down this with my little eye, right? Got a little eye, and that's a pretty flat eye. There we go. Okay, and then here's my And I see here on this terminal that I have a nice anti-addition, right? So when the base comes in, I'm gonna get elimination. So it has to be anti-fair planar, right? If we look at the other possibility, one of these two hydrogens, so now we're looking this way. Now when we look at the Newman projection in the front here, I have my hydrogen. Now I have my CH2, right, and my CH3. I have my other hydrogen. Now I've got my nitrogen. I'm going to draw it out a little differently so you can kind of see what the point is here. That when you make this quaternary salt, that nitrogen is tetrahedral, right? And so now what we have is the problem with our steric hindrance. So what's happening is if we look at this red one here, the Satsev product is going to have a higher transition state, right, than the Hoffman. And this wasn't the case whenever we looked at the tosylate or a different leaving group, right? Because we don't have that big quaternary ammonium salt. The big quaternary ammonium salt is what's going to drive the difference in our transition states here, and is going to drive the Hoffman as the product by lower transition state. Okay, and this is a case, if in this case we have the methyl, the terminal, but in any case in this, right, you're going to have lower steric for the one that is least substituted, right? So the more substituted, so we're going to drive the Hoffman products with the ammonium complex, right? So let's look at one of these. Okay, let's go ahead and take a look. So on this one, right, we have two possible products. We have symmetry down the middle, so we could lose one of these two hydrogens, which is the same as these two hydrogens, right? Or we could have lost these hydrogens. The one going up is going to be my Hoffman product, so that's going to be the favored product. Right. So this is going to go back to alkene preparations, right? And you're going to need to think about now which is going to be the product. So whenever we were doing that in organic one, we were always looking for the CHEM3153002. Now we're reversing it. We're looking for the Hoffman, right? So a little bit different. And then the next one, if we look at that, it's actually going to be this double bond here. That's going to be the Hoffman one. Right. So if we look at it, we've got these two hydrogens. And we had this hydrogen, and eliminating the purple ones give us the least substituted product, give us the Hoffman product. Okay. So Hoffman eliminations give you Hoffman products. Okay, questions about those? And we are getting in, we're getting close to the end of the semester, and the final will have, right, it'll, because we've gone through so much of this, you're going to see quite a bit organic one. It's kind of come out organic. That's a horrible word. The organic reactions are coming out organically, but as we go through, we reintroduce some of these reactions from organic one, right? So we're not going to pick on those, but as we go through, you'll see that we've actually probably touched almost all the reactions from organic one by this time, right? And we're going to see a couple more as we go through. The next reactions have to do with nitroso acid or nitrous acid. So we're used to nitric acid, that's this compound. Nitrous acid is this compound, right? So we've got one less OH on there. And the thing that we want to look at for this one is that this nitrous radical is usually given in this form, right? So like sodium nitrose, that if we put sodium nitrite in HCl, this is the way you're going to see it most often, you end up with this nitroso ion. So the way we're going to be using this is we're going to react these with amines. So if I have a secondary amine, I'm going to add the sodium nitrite plus HCl. I'll end up with this nitrosoamine. So sodium nitrite, anybody heard of that? Nitrite or nitrate? Right, so nitrites and nitrates are used in curing meats, right? They're also a natural byproduct whenever you barbecue meat, that little red line that they usually see in truly barbecued meat it comes from this process. And then there's nitrosamines actually turn out that can be in high quantities can be problematic, right? So, and part of that has to do with the nitrose. It also turns out that nitrosamines are necessary in some biological functions. So this isn't an artificial molecule, but in high concentrations, it can cause problems. So there are people that say you should never eat bologna. You know, cured meats are bad for you. This is one of the reasons, right? Is this nitrosamine compound. But you know, salami is really, really good, and I'm not giving it up. So, but sometimes you just have to make choices. Okay, the way this works is that the nitrogen here reacts with the nitrogen with the lone pair reacts with the nitro and the nitroso ion. Right, and then the water in the solution or another base pulls this off. Usually there's a little water because of the process in forming the nitroso ion. So nitrosos do have biological functions. They are a byproduct of smoking meats or preserving meats with nitrate type compounds. The bigger reaction that we're going to be focusing on is actually primary amines. With primary amines, we end up with a so again, sodium nitrite, an acid, so here we end up with a diazonium. So working through the mechanism, lone pair, just like before, attacks that. We get the CH3, N, H, H. Then we get a proton transfer. So water picks up a proton. Then we get another proton transfer. End up with this compound. We pull proton. We get another proton transfer. Then the lone pair comes down, kicks off water. Starting at the beginning, right, we get a nucleophilic attack on the electrophilic nitrogen. Then we get a proton transfer, proton transfer, proton transfer, another proton transfer, and then loss of the leaving group, which is water in this case, to get us to a final product. Okay, questions about that one? Turns out that alkyl diazoniums aren't overly useful because they're not very stable. Okay, so this alkyl group, right, that decomposes really quickly. To form the carbocation. So synthetically, these aren't overly useful, but I mean, this would react with almost anything around, right? Where these have been used scientifically has been to look at carbocation spectroscopy, because you know, if you heat this up to a certain temperature, it'll form the carbocation, and then I can study the carbocation. But synthetically, they're not overly useful, right? But I can make the diazonium. Usually you would do these cold, because if you warmed it up to room temperature or above, they're going to decompose real quick. The aerial diazoniums are much more useful. So if I take an aniline, right, react that with sodium NO2, it's going to form the same diazonium salt. But then this reaction to the carbocation won't occur, right? Because that's a secondary aromatic, that's an sp2 aromatic carbocation, which isn't stable. So therefore, this is a much more stable group. So for alkyls, they can form, right? But we're not going to be doing much with them after forming them. But for the aerial diazoniums, there's a whole set of chemistry around forming the aerial diazonium salts. The first class of these is going to be the Sandemeyer reactions. So once we form the diazonium salt, if we react it with copper bromide, copper iodide, copper chloride, or copper cyanide, so you can kind of see where this is going from, copper 1 salts. Here, what happens is I substitute directly for the diazonium with the bromide. In most cases, these are kind of coupling reactions, or with the copper, it's a coupling reaction. Right. And then very uniquely, right here, I can add a cyano directly. So I know of ways to make the bromide. I know of a way to make the iodide, the chloride, but this one is unique, right? Adding that cyano to the aromatic. The Sandemeyers, the commonalities, they're all copper 1 salts. The next reactions are also named Schinman reaction. So if you notice above, there wasn't a way to make the fluoride. Because of the copper. So here, if I take HBF4, so fluoroboric acid, that'll make the fluoride. If I want to make the hydroxyl, this one doesn't have a name, but if I want to make the hydroxyl, I take the same diazonium salt. Again, remember, this is unique because making the hydroxyl can be difficult. The way we know how to make a hydroxyl at this point is nucleophilic aromatic substitution under extreme base conditions. Here, if we make the diazonium salt and just add water and heat, we can make the phenol in much less harsh conditions, right? So synthetically, this is a useful process. We can also use the diazonium salt with phosphorus acid. Okay, so notice just two oxygens there. Oh, that's ugly. They had the hydrogen. You might ask why that would be useful. That could be useful if I wanted to do something this could be useful by the nitro group has a meta director. I could add the 2 bromines to get me meta. I couldn't add 2 bromines to not be meta, right? Because a bromine is an orthopair directing group, right? So that gives me my selectivity. And then here I reduce the nitro down to the amine. I pour the diazonium, and then I replace the diazonium with a hydrogen. Now I have that 1,3 meta dibromo species that I couldn't make if I was just using bromine. So I use the directing effect of the nitro, and then I remove it. I could also use a nitro or an amine as a blocking group, kind of like I did with the sulfuric acid. Remember, I could make a sulfonate and then remove the sulfonate with acid and water. So it gives me a directing a group effect on the ring. Questions about these diazonium salts? So let's try a few. Okay, let's take a minute or two, try these. Well, let's take a look. Okay, so the first thing on each of these is you're going to make the nitroso, the diazonium, sorry, the diazonium. So you're going to react it with the sodium nitrite in acid. And then here we want to end up with the OH. The hydroxide, we just add water and heat once you form the diazonium. And it does direct substitution, so I don't have to worry about changing my arrangement around the aromatic. Second one, again, we want to form the diazonium salt, so sodium nitrite and HCl. And second, here we're going to add the copper. This is one of the Sandemeier's. So copper 1 chloride. Then last one, again, we make the sodium nitrite. And here, this is not one of the Sandemeyer, so this is HBF4, so tetrafluoroboric acid. Questions about these? Next section is azo coupling. We take the diazonium salt we can react with an aromatic. R usually needs to be some type of activating group, so hydroxides, methoxides, nitrogen containing compounds are all good. Okay, that's going to give us an azo compound, the way this works, and I'm going to use the phenol here for this one. Lone pair comes down. It's going to react favorably at the para. Ortho's also okay, but again, we got a lot of sterics with that large diazonium salt there, so it usually goes para. All right, so this is an electrophilic aromatic substitution. And then here, we just need a base, and here any base could pull that off, even the chloride. But once we pull that off, right, we regenerate the aromatic. So this is AES mechanism, right? Aromatic electrophilic substitution. Where you see a lot of these is azo dyes. We think about this as got a long conjugated system, which brings it into the visible. But if I do something like this, you end up with something that's kind of a push-pull system. So if we think about it, this can push and pull electron density from one side to another. So a lot of our kind of the basis of artificial dyes was these azo coupling compounds. Some of the red colors that have been problematic, so they got rid of, I don't know if you remember, probably not, got rid of red M&Ms for a while, right? Well, they had to replace the dye they were using for the red M&Ms because the red M&Ms were a diazo and it turned out to be potentially carcinogen. So you couldn't use it in food products anymore. Whenever Paris was known as the city of lights, Berlin was known as the city of colors. This is way back in the late 1800s. That's because they had come up with artificial dyes. And these artificial dyes were based off of this azo coupling compound reaction they came up with. So they were able to make blues and purples and all kind of different colors that up to that time weren't available. Purples really only came from a form of sea snail, and it might take 10,000 to come up with a couple of ounces of purple dye. That's why royal purple, it was really hard to get. Blues also were really hard to get, right? So certain colors were really difficult to get. Once we started to get artificial dyes, and the azo coupling was the beginning of the artificial dye industry, then you could have any color you wanted, right? Most people, what colors would you have? Red, if you lived in a place with soil like ours, right? Green, that's pretty easy, right? Browns, that's what color the fabric is anyway, right? So most of the people had kind of earth tones, and that's because that was what was available. Once this came out, you really started to get very vibrant colors on everything. And then that led to large chemical industry in Germany as well as other places. Okay. Heterocycles, we've seen these before, right? We've got the nitrogen containing pyrrole. If you put two nitrogens in it, you can end up with a imidazole. And then we know pyridine, we've seen that one quite a bit. Now, most of these, they're biologically active, they're important molecules. They usually are proton sinks, right? So they can accept a proton, give away a proton. When you see pyrrole in a molecule, sometimes it's a positive proton, meaning it's gonna give away a proton. And when you look at pyridine, it's going to accept a proton. But there are a couple of reactions. These will react as aromatics, right? So this is aromatic. So all of these are aromatic groups. And if we take pyrrole and put it in with bromine at a cold temperature, we can get electrophilic addition at the 2 position. If we bring in pyridine, we get a similar reaction, but now we have to add a lot of temperature. And we get the 3 position. So if we think about pyrrole, it acts, it behaves, right, like an activated aromatic, right? So you can think about it, it's adding to the ortho position and it's very active. I can do this at cold temperature, where the pyridine behaves as a deactivated. Again, if we went through the mechanism on here, you see why this one forms in that 3 position versus a 2 position, which is very similar if we had a nitro substituted benzene, right? And then we need a much higher conditions, again, acting like a deactivated aromatic. So when you look at these two, this is there's not a lot in the chapter about this, but this is the takeaway from these, is that one is acts very much like an activated aromatic. You'll see this a couple of times in biochemistry mechanisms, and then pyridine acts as a deactivated aromatic, but both do aromatic electrophilic substitutions. Now, what we have done by finishing the amines chapter is actually add a whole bunch of synthetic strategies, mostly because of this diazonium salts, right? So now we have a Hofmann elimination process, right, that we didn't have before. And now we have lots of ways to go back and look at our aromatic electrophilic substitutions and form a lot. So what we'll do to end out today is we'll look at some synthesis. And we'll start by me just giving you the synthesis, and then we'll look at a couple. So now what we've done is gone from 1, 2, 3 step synthesis to potentially getting to 4, 5, 6 step synthesis. Again, take it step by step. Don't think you can get all the way to the answer. And feel free to look at your notes, talk to your neighbor. Okay. So let's start to break that down. If we add HNO3, right, going back several weeks, right, that's going to be nitration, right? We could also have some ortho, right? But with the propyl group on there, the pair is probably going to be the major product. Then what happens when we do hydrogen and palladium on carbon? Okay, we reduce that down. To the amine. And then what happens with sodium nitrite, NaCl? We form the diazonium. And then what happens when we add the copper bromide? Okay, we replace the diazonium with the bromine. Okay. Questions about any of those steps? Okay, on this bottom one, the first thing we're doing with the acid chloride and the pyridine is we're going to be protecting that amine. Why do we need to protect the amine? What would happen if I added chlorine and AlCl3 with an amine? AlCl3 is a Lewis acid. Amines are Lewis bases, so the amine would react with the aluminum and form a positive. What happens on a ring directing effect if I have a positive nitrogen? Positive nitrogen is a meta director, right? So if I want this to go to the ortho para position, and again, we'd have this plus a little bit of the ortho. I can get the chlorination, right? What happens with H3O plus? Right, I've got an amide and I've got a chloride. H3O plus and amides will hydrolyze that amide. And with the H3O plus, I'll get the positive here. That won't matter too much because the next step is also in acid. That'll form the diazonium salt. And then what does water and heat do? And that replaces the diazonium with the hydroxide. Questions about that sequence? Okay, let's try a couple more. This time, give the reagents necessary. Okay, let's take a look. All right. So whenever I'm giving you the reagents, right, you work through it. But here we have to think about multiple steps and synthetic strategies. Here we're starting with a ketone. Well, what do you notice about the product that should give you a key to what we need, where we need to go? This is an alkene, right? But what type of alkene? Is it the most substituted or least substituted? This is a least substituted, right? So that suggests that this is a Hoffman alkene, right? So if it's a Hoffman alkene, what's probably the way we need to get there? Through the Hoffman elimination, right? Which means at some point, I'm probably going to have something like this so that I can end up with a Hoffman elimination. Oops. Let's move that out of the way. All right, so how can I go from a ketone to some type of amine? Right, I can do that with a reductive amination. And there's a couple of ways we can do this, right? I could use the secondary amine with trace acid and then the sodium cyanoborehydride. That'll give me this. And then if I take that first step, CH3I in excess, that's going to form the quaternary salt. And then second step, silver oxide and water with heat. And that'll eliminate. I could have used here, I could have used the primary amine. So if you use that, it do the same thing. Here I'm just using a slightly different amine. So I could use the primary, secondary, ammonia, but the process would be the same. In the second one, I'm forming the diazo coupling, right? So therefore, I know what reaction I have to use. I have to use the diazo, right? So I'm going to be using the azo coupling. And in the azo coupling, there's two aromatics, right? And I potentially could form, if we think about it, I could form this side plus this, right? Or I could have had this plus this, right? So for the azo coupling, what's one of the driving factors we want? Right? One of the driving factors, it needs to be an activated aromatic, right? So something with lone pairs like an oxygen or a nitrogen. And what is its directing effect? Is its directing effect meta or is its directing effect ortho, para, mainly para? It's going to be para, right? So if we look at these two possibilities, would this one give us the meta positioning? No. Does it have a lone pair that makes it very activated? No. How about this one? Do we have a lone pairs on the oxygen? Yes. Would it add to the para position? Yes. So therefore, the second set is what I want to use. Right? And so therefore, the only thing I need to add to this is the diazonium salt with that meta arrangement. Okay. Okay. Questions about that? Okay. So we will have